1 second. Window. Okay, so can you guys see my screen?
Yes.
Okay, cool. Okay, can you see the slideshow mode being enabled? Can you see the whole slide?
Yeah.
Okay, cool. Yeah. So yeah, sorry, typo. It's actually session 3, not session 2. My bad. I'm just gonna type 3 over here. Yeah. So it's for those of you who attended the first 2 sessions, my co-mentors Harshit and Aditya would have gone through a basic introduction on microcontrollers, microprocessors, and even one of the a basic introduction to one of the most popular microcontrollers in the world right now, that is the Arduino microcontroller, and basic syntax on how to work with its IDE and stuff. So that's actually it's pretty nice that you guys are learning this in first year itself, and it's pretty actually it's a very interesting thing to work with the Arduino Uno or the other Arduino microcontrollers like the Mega, the Leonardo, etc. So the Nano. But the thing is, once you have a microcontroller with you, you also need, like, you know how to program them, but you also need specific hardware, right? So I need, for example, if I want to automate my whole home, my house. Okay, so if someone tries to break into my house, I want to have a burglar alarm which starts beeping and then alert me in the middle of the night. Or if suppose I put on the water pump and I need to know when should I switch the water pump off. I need some if instead of keeping a timer or checking on the water pump level regularly to decide whether to turn it off now or not, I can just automate the whole thing, and then I can you know I can either actually make it tell me when to stop, or I can actually automate even the mechanism of stopping the water pump altogether. So there are various uh, possible ways of exploration which you can do in terms of automation of systems. So as I said, all these needs a specific set of hardware. Okay, so hardware can basically be either sensors or actuators. So let's learn in this session we'll basically be getting to know the most frequently used sensors, actuators, and communication protocols. And what is a communication protocol? So basically, suppose I have hardware. I need the hardware to communicate with the microcontroller or the processor at hand. So how does it communicate? It uses communication protocols. So the protocols ensure proper, like stable and yeah, efficient communication between the hardware and the software, that is the processor, which is embedded into the processor or flashed into the processor. So that's how the whole thing works as an automated system. We'll understand the basic functionality of a few sensors, actuators, and a few communication protocols as well, and we'll also understand how to integrate all of them to form a robot or an automation system. Yes. Does someone have any doubts? Yes, I'm recording the session. You can find the recorded version on YouTube, which will be uploaded later. Okay, cool. So understand. Okay. Okay, so let's start with sensors. I mean, I don't really have to explain what a sensor is, because I'm pretty sure most of you would have seen sensors in real life as well. However, we'll just go assuming everyone is assuming like there's someone in the meeting who's at the beginner level. We will start off with that stage itself. So a sensor is a device which always used to convert a physical quantity. Say, for example, if I assume a human being, right? A human being can easily gauge how far they are from a specific obstacle or a specific. If someone asks me how far away are you from the blackboard are you when I'm sitting in a classroom, I can say I am approximately this many meters away. I won't be able to tell the exact value, but I can tell an approximate value because again I use this processor which is called the brain, and I have sensor which is the eye. So the eye is able to sense I have two eyes basically, which enables three-dimensional perspective, and using this sensor called eyes, I use it, and then I process it in my brain, and that's how I get to know that I'm approximately 3 meters away or 2 meters away. So basically, this is with respect to any human being or a living thing. But when we want to use, like, make a robot which is essentially tries to mimic the same actions of a human being, a sensor is basically a device which is used to convert a physical quantity to an electrical signal for the purpose of measurement. So basically, if I have a sensor and I want to measure the distance, I'm going to somehow convert that physical parameter into an electrical signal, which will be then fed to a processor or a microcontroller, and then the algorithm which I would have dumped into the microcontroller will use that data to find out various other things, or maybe decide what next thing should be done. So sensors, obviously, there are various physical quantities which a sensor can detect. The most common ones being like proximity slash distance slash orientation. Sorry, when I say orientation, when I say orientation, I also mean at what angle something is with respect to a frame of reference. So it's like the XYZ axis as well as the angle between some if I draw a line somewhere in 3 dimension, at what angle that line is making with respect to the XY plane or the YZ plane or the ZX plane. All these things can be are part of the orientation of the line, right? So similarly, I can find the orientation or the proximity or the distance of an object with respect to a frame of reference. So that is basically a physical quantity which a sensor can be used for. The next is obviously a light or image, which when I say light is basically an electromagnetic wave. It's like a series of photons. So the the reason why I say image is because when I say a light sensor, we usually refer to a camera. So that's why a camera is used to detect an image and capture the image and store the image inside a storage in the form of electrical signals. So light or image is another physical quantity as well. And the next is temperature, humidity, which is again quite important as well, because we can, if I say I want to switch off a fan when it's too hot, but I'm too lazy to get up off my chair and go and switch on the fan, I can automate it by doing by attaching a temperature sensor near me or in the proximity of where I am, and then automate the whole thing. So a sound sensor, that's also something we also known as a microphone in other words, and as a sound sensor senses sound, which is basically a wave as well. So electrical quantities like voltage, current, resistance, resistivity, there are like so many other electrical parameters as you guys would have known. So we use sensors to detect even those electrical quantities itself. And of course pressure, stress, strain, the various mechanical quantities which are used sorry, yeah, so the pardon me, so that even force, pressure sensor, actually the pressure sensor is also called as a barometer, and then stress, strain, and all those things can be measured using sensors as well. So and many more such physical quantities can be measured using sensors. It's not just limited to these. So like there are like hundreds and thousands of sensors available in the market. You can just like depending upon what quantity you want to measure, and each and every one of those sensors internal circuit is completely different. None of them will have a very like, you can't say all of them have like a basic same circuit. Like that circuit depends entirely on what the sensor will be measuring, and also the communication, like how is this measured data being communicated with a specific processor or a microcontroller. All those things will matter. So let's start with the first category, that is proximity slash distance slash orientation. So if you guys remember, I told you earlier that this is an interactive session and not something which I'm not a faculty who's coming to your class and teaching and who will start beating you with a cane if you start speaking. I want you guys to speak. So please interact and let it be an interactive session. So can you guys name, whoever knows any of these sensors, can you guys just tell me which sensor is which? What is the name of this sensor? Each one of these. Yeah, the first one is ultrasonic, correct. What do you guys know what the last two are?
Is the second one sound sensor?
It's okay. Yeah, it is actually a sound sensor. You're right. So it's basically sonar. sound navigation and ranging sensor. That's absolutely right. So this is HCSR04 sensor, which is like almost every single robotics enthusiast will know, and we would have all worked with it. So it's a pretty popular and famous sensor. The second one is it's the last two sensors are both produced by the same company called Robotics. It's a sonar. Sonar stands for sound navigation and ranging. It is again a proximity and distance sensor itself. It's not a sound sensor. It just uses sound to emit. I mean, ultrasonic sensor also uses sound, but these two are the last two are less known sensors produced by Robotics. These are much more expensive and advanced as compared to the HCSR04. So technically, you could say the first one is also a sonar because it uses ultrasonic sound to emit to find the proximity or distance. But yeah, so all of them are basically to use sound waves for the purpose of recognizing distance or proximity. So yeah, you can also see the pin diagram over here, like VCC, trigger, echo, ground. I mean, the pin diagrams are not visible here, but they're not really as simple as this. It's a bit complicated for these two. So for this, I'm not really sure about this because the pins are not listed here. I haven't personally used this sensor myself, but these two are very expensive. So I would suggest you guys start off with this sensor itself because this is a very good start for starting off with your robotics hobby projects. So the obviously VCC stands for the 5 volts voltage, and the ground is the common ground of your microcontroller or processor. The trigger and echo pins, can someone tell me what these two are used for? Whoever has used this sensor before.
Trigger is to switch on the ultrasonic sensor, and echo is to tell it to
receive, right? Yeah. So so they say that's right. So basically, you're gonna emit using the trigger and echo pins. You're gonna using a microcontroller. You're gonna signal this trigger pin, and once you do that with 5 volts signal, and once you do that, the ultrasonic sound will be emitted from the emitter, and once the emitter is gonna emit the ultrasound, and then you have to wait for some time. Like you should generate a pulse. Basically, a pulse is like a low signal, and then a high signal, and then a low signal. So a pulse of ultrasound has to be generated, and then the echo will basically be an input pin. So the echo is going to receive the the sound, the reflected sound waves back, and once it receives it back to the microcontroller, you can find the distance. So can someone tell me how does emitting sound and getting the sound back have anything to do with finding the distance between the sensor and an obstacle in front of it?
time taken for the sound to bounce back, and then it's calculated.
Yeah, correct. So you have the time. The time will be calculated from. That's absolutely right. So you're gonna emit something and calculate the time for the receiver to receive the sound. And once it does that, you're gonna find this thing like the distance. So speed is equal to distance by time. That's the basic equation we all know. The speed of sound is fixed. It's a constant value. We all know what it is. So we know the speed. We know the time. Which will be calculated by the processor. So the only thing which we have to find is the distance. So distance is equal to the speed multiplied by the time taken, and using that we can find the distance between the obstacle which is in front of this the sensor and the sensor itself. Sorry. Although there's one disadvantage of this sensor, that is mainly, so suppose I keep something which is very shall I put it? Okay, so suppose I put an obstacle exactly in front of the emitter and completely block the emitter completely. I completely block it so that there's no gap between the obstacle and the emitter, or even if there's like minute amounts of gap also, that's fine. What's gonna happen in that scenario?
There's no space for the sound to reflect back into the receiver.
Yeah, exactly. So the sound which will reflect. Guys, I think only one person is speaking. I would request all of you to speak up. It's totally fine if you get it wrong. No one's gonna scold you or judge you on that. That's how we learn. We make mistakes and we learn. So that's totally fine. So yeah, we keep an obstacle in front, and then once the emitter emits the sound, it's gonna get reflected back onto the emitter itself, or maybe over here and all, but it won't really reach the receiver. So that's not gonna work out. So that there is a minimum range for this sensor, so that it can detect something only if that something is kept at least a fixed distance apart from this, and there's a maximum range. I mean that this applies to all the three sensors actually, not just this sensor. I'm sorry, it applies to all the three sensors as well. So all of them have a minimum range and a maximum range, within which only it will function properly and with complete stability if the whole obstacle is kept completely outside this range, minimum and maximum range. Then it won't give you, even if it gives you the values, it will be completely inaccurate and wrong values, and it won't be right. So always remember to keep a check on the range before you use a sensor for your application. So this is basically, so this is basically a basic brief overview of how it works. There's a sender or
One second, actually.
yeah.
Can you go to the previous slide? Here in SR04, there are
Yeah.
two blocks. One is for receiving, other one is for emitting.
Yeah.
But in I didn't understand that. So is it like one for emitting or one for receiving or something like that? Huh?
Yeah. So do you mean the trigger and echo pins, right?
No. I mean these two
These
circles
two
over
things.
here.
Okay, one is for emitting, one is for receiving. This always emits the ultrasonic waves,
Oh.
and then this always is used as to receive. It doesn't emit anything, and this doesn't act as a receiver. This only acts as an emitter, the left one.
Oh, okay. Then in MB1240 sonar, in that there's only one block. Why is that? Like, does it do both the emitter and the receiver work at the same time? Is it?
As far as I know, it has both. They've tried to overlap it as much as possible. So that's the advantage of this MB12240 compared to this one, because this gap will definitely ensure that the minimum range of the sensor at CSR04 is greater than the minimum range for this MB1240, mainly because of the overlap happening between the transmitter and receiver. So that's an advantage of this sensor.
Perfect.
Yeah, so as far as I know, that like the distance between the transmitter and emitter and receiver on the MB1240 and MB7173 are much lesser compared to the one for HCSR04. So that's a major advantage these two sensors have.
Yeah, got it.
Yeah, cool. So if you guys are curious about these sensors, definitely check out the data sheet. There's like so much information there. Like due to the lack of time, I can't really go in depth into these sensors, but do check out the data sheet online. So this is basically how the functionality is. The sender and or receiver is over here. It emits the sound waves, and then once the sound waves hit the object, they reflect back, and the receiver receives it, and then the distance r is used, and the time taken is calculated, and then thus the speed is known and the time t is calculated, so the distance r is measured from this. So yeah, here we come to another set of proximity sensors itself. It's not a different physical quantity. Again, let's start. Someone name all these sensors for me. Like even any one is fine, not all of them, if you guys don't know all of them.
First one's infrared sensor, I think.
Yeah, that's correct. First one is the infrared sensor.
I think second one also is infrared.
Which one is this?
Infrared, I think. There's a transmitter in this field. I'm not sure.
Okay, that's fine, no problem.
Is the last one a camera?
Yeah, it is a camera, but it's a special type of camera. It's not the traditional camera which we use.
I think the bottom middle one is LiDAR.
Okay, that's very good. Yeah, that's very accurate. Correct. So
Is the second last one a servo motor or something?
no, a servo motor doesn't really look like this. It's I'll show you a servo motor how it looks and how it works later onwards in this session. But this isn't a servo motor. It's a LiDAR, as someone said. It's actually okay. Shall I show the answers, or does anyone else want to try? Okay, so I'm gonna show the answers now. So the first one is an IR sensor, the typical common IR sensor which we use. All these three are LiDARs only. Okay, so the LiDAR stands for light detection and ranging. light detection and ranging. So basically what lidars do is they emit infrared rays or electromagnetic waves of specific frequency and wavelength, and they again it's very similar analogy to the ultrasonic sensor where they have a an emitter and receiver, and an emitter and a receiver over here as well, and even the IR sensor also has an emitter and a receiver. So all of them, these sensors, they emit IR infrared, and then they receive the infrared, and they use the same analogy as ultrasonic sensors to find the distance between the sensor and an obstacle in front of them. So yeah, so this is the TF mini lidar. Okay, this actually I'll tell you, the IR sensor is the cheapest among all of these. The TF mini lidar is the second cheapest among all of these. The lidar light V3 is the third cheapest, and okay, and among these three are one of the most expensive ones of comparing on this whole slide. These three sensors. So I'll tell you more about that, these two, but first let me tell you what an RP lidar is and how is it different from these two lidars or the IR sensor. So an RP lidar, as you guys can see, it's basically it looks basically like a cylinder or a drum sitting on a platform, and you guys might be wondering how does it really work. So basically, these sensors, right, the ultrasonic sensor, the TF mini lidar, IR sensor, lidar light V3, and even the sonar sensors are all unidirectional sensors. The reason why they're called unidirectional sensors is because if I point them at a specific object, they can only, the field of vision is so negligible that they almost detect only in a straight line. It's unidirectional. So the field of vision is like almost maybe like 1 degrees or 0.5. I don't know the exact values, but the field of vision of those sensors isn't really that high. They can't cover a large area and identify the distance between the obstacle in that large area or something like that. They only focus on one specific obstacle, due to the lack of field of vision. They're unidirectional. They can only focus on one direction at one time. So suppose I have a robot car and I attach an ultrasonic sensor or maybe even the TF mini lidar in front of the robot facing forward, and an obstacle is gonna come at a 45-degree angle to that sensor. The sensor will not be able to detect that object, and the car will crash because the object might still be close enough to hit the robot. So that's why these are unidirectional sensors, and the disadvantage mainly is that they don't have a huge field of vision and they can't be used to detect obstacles all around. So to overcome this problem, these three sensors are present, these three proximity sensors. This one, the RP lidar, is basically has a field of vision of 360 degrees. So I'll actually I would like to show you guys I'll probably show a video on how it works so that you guys can comprehend it much better. RP lidar working. Okay, so this is how the RP lidar. Can you guys see this? Is this visible to you guys? Hello.
Yeah.
Okay.
Yeah.
Yeah. So as you guys can see, this is another version of the RP lidar which I showed you a picture of, and I'll just show you how it works. 1 second. Okay, this is how it works basically. Can you see the lidar rotating? It basically rotates 360 degrees continuously like this. Basically, it keeps rotating like this again and again and again. And what it does while rotating is basically it emits infrared rays once again. It's not a different electromagnetic radiation. It's the same thing, infrared. So it emits IR radiation throughout the 360 degrees field of vision, and it also has a receiver. There's a transmitter and a receiver on this as well. Due to the extremely high speed of rotation, it keeps sending the IR rays like in all direction at every single possible direction possible, and then the receiver keeps receiving the rays which after emission hit an object or obstacle reflect back and hit the lidar back. So these rays are received back by the lidar, like the RP lidar, and it keeps on happening in a loop, in an iterative loop, again and again and again. And thus what happens in the end is, so once the emitted IRAs hit an obstacle and they come back, there's a specific time taken for the rays to be emitted, hit the object and come back. So this time is considered by the processor or the microcontroller, and even the frequency and the wavelengths of the rays which are emitted sometimes changes when it hits an obstacle or an object. And so when the lidar receives the rays, the change in frequency or wavelength is also considered or taken into account. And using all of this information, it can not only find the distance between each and every single object around it, it can also help in finding maybe the orientation as well. So I'm not going to go completely in depth, because usually we use lidars for the purpose of SLAM. Okay, SLAM stands for simultaneous localization and mapping. That is a concept for another day, but that is one of the main applications of this 360 degree rotating lidar. So can someone tell me there's a 360 degree field of vision for this lidar that's pretty impressive. It can find the distance and orientation of objects throughout, in all angles with respect to this frame of reference. So what could be what is the still a disadvantage for this lidar? If I keep this lidar on a robot, what could still go wrong? What could be a disadvantage? Can anybody, why do you think we really need these two things, these two sensors?
I think the last sensor has like gyroscope and all that to find the sensor in 3D. This one finds the position of objects only in 2D.
Yes, that's
Is it the range?
yeah. So the answer is correct. It's because of the limitation of dimensions. So this RP lidar can only it can focus on 360 degrees, yes, but it can only focus on a two-dimensional plane, that is the plane of the rotating cylinder. So it's basically like I think I'll just show you. Yeah, something like this. So basically, if I keep a lidar on the car, right, I can only find obstacles at the elevation of the car. I basically can only find are you guys visualizing what I'm saying? So if I keep the lidar on top of a car, it can only sense the top of other cars. It can't really sense for example somewhere near the sky at an angle of 45 degrees near the sky, or 60 degrees near the sky. It's the whole sensing is done on a two-dimensional plane which is parallel to the ground. This 2D plane is elevated a bit from the ground, and it's just kept over there where the lidar is. So that whole sensing is done exactly on one plane, and anything below that plane or above that plane isn't really sensed. So that's one of the main disadvantages of the RP lidar. So what some people have done to counter this is they've made a few sensors like the RP lidar, but they've also attached a translating joint kind of a mechanism below it, such that during the whole rotation it kind of pushes the lidar up and then brings it back down continuously, so that basically it gets a whole elevation as well. But still doesn't give you a whole the field of, I mean, depending upon the speed of the translatory motion and depending upon the how high does it the translation joint take the lidar up, the elevation and all depends upon that. So basically that's one of the main drawbacks of the RP lidar. But then RP lidar is super expensive and it's super advantageous as well, because of the high and the very good resolution it offers. Usually most lidar sensors and infrared sensors offer very good resolution when it comes to the images and the mapping or done of the environment. But again, I'm not going to dwell into mapping, because SLAM is another ocean to explore. So I'm gonna get back to you guys on that on another day. But you guys understood the basic functionality and the basic drawbacks of this sensor, right? So that's I mean, do check out various projects and various videos and articles on the RP lidar. It's a very popular and booming sensor, I could say. So now these two these two sensors is basically I haven't really used the Intel RealSense, but I've been using this Z stereo camera for the past 2 years myself, and to be honest, I might be pretty biased, but this sensor is one of the most user friendly and convenient sensors I've ever used. It's also as equally expensive as well, and you probably might not find this in India. I don't really. The last time I used it, I had to import it from the US. But anyways, so this is the Z stereo camera, and this is the Intel RealSense stereo camera. So what does stereo cameras do? So as you can see, like unlike a traditional camera, these have not one but two lenses. There's one lens here and one lens here. This actually has like three lenses and one I'm sorry. And if I'm not wrong, this is an IR infrared emitter as well. So so the reason why we prefer stereo cameras compared to an RP LiDAR or these unidirectional LiDARs is pretty obvious. These offer three-dimensional field of view, right? So the only thing is, why can't we just use a mobile phone for that purpose? Because if I use a single lens can only tell me the x coordinates and the y coordinates, that is the upwards and the up down and left right kind of a thing, but it can't really tell me how far an object is. So if I use a mobile phone and show it at my friend's face, I can't really predict how far my friend is just by looking at the image on the mobile phone, because there is literally no information whatsoever on the depth. It's only the x and y two-dimensional data which I have. So that is literally why stereo cameras exist. So stereo vision, what it does is it takes an image from both these lenses. So it captures an image from this lens, it captures an image from this lens, and then it combines both these images using various mathematical operations involving convolution, triangulation, etc. And all of these mathematical operations are used, and in the end these two images are combined together to form something called as a disparity image. Okay, so a disparity image, and this disparity image basically is I'll just can you guys see this? Okay, what exactly is this structure over here?
Colosseum.
Yeah, it's Roman Colosseum. So guys, also one more thing, even though this session will be available to you recorded later, I would suggest you guys make notes if you because some things are not listed in the PPT. So that's because I wanted, I didn't want to put too much text in the PPT because it will bore you guys. So just make sure that you some things which I'm explaining, if you feel it's more relevant, or if it's worth noting down, you can type it in your laptop or something, or in the notebook, or if you want, the recorded session will be available later onwards, you can use that also for reference. So this is the Roman Colosseum, right? So essentially what this there's something kind of weird about this Colosseum. It's not essentially taken from a normal camera, right? It's not man-made completely. Nobody has drawn this picture. It's actually obtained from the real Colosseum itself. So how did they get this? So the thing is, what they did is they just used stereo vision, okay, and then they generated a disparity image, and from that disparity image they generated this. This is called a point cloud, point cloud. Point cloud. So a point cloud is essentially a three-dimensional representation of an object completely made up of points. So as you can see, every single thing in this whole picture is comprises of dots or points. Like it is basically just dots which are staggered everywhere and like stacked upon together. There is no line, a continuous line or a continuous curve over here. Everything is just a dot. So basically that's essentially what a point cloud is. A three-dimensional representation made completely with points is a point cloud. So as I said, it's a three-dimensional representation. What I'm showing to you right now is a two-dimensional image, but if I actually use have access to the software when they actually made this point cloud, I can actually use my cursor. I would have used my cursor to move around this Colosseum everywhere. Like I can zoom in, zoom out. I can actually, and if I use an Oculus Rift kind of a AR VR headset, I could have actually seen a three-dimensional view of this. So this point cloud is not a 2D image, it's a 3D representation. The data is completely three-dimensional, which means the x coordinates, y coordinates, and z coordinates. That is, so for example, assuming the top left of my screen is the origin, if I move from left to right, it's the x-axis, and if I move from the top left to down, it's the y-axis, and the depth, that is how far each and every point, like the the straight line, is the z-axis. Then using xyz coordinates, I can find each and every one of these points, right? So each and one of these points has its own xyz coordinates, and that's exactly how this whole point cloud has been formed. Okay, so that's how we use stereo vision cameras or even RP lidars. So the thing is, if we use an RP lidar, we can still make a point cloud. Okay, but then the problem is it won't be three-dimensional. I can just see lines. I can just see a circle, like a circular plane, and on the boundaries of the circle, sometimes like I can just see dots over there, which essentially means that an obstacle is over there in that by that boundary. And if for example, if I use an RP lidar over here, so this thing, I'm trying to detect this car, right? Okay, I apologize, I said point cloud is a three-dimensional representation. It's only three-dimensional in this scenario. It's not necessarily by definition three-dimensional. So if I use a lidar over here and I try to recognize this, I can see dots all over here, the boundary. I can see this whole boundary will be made up with dots. I can't really see any of this car, because once the lidar, the infrared rays hit this car, it will come back to the the receiver on the RP lidar. So it won't necessarily see all these things. This headlight over here, the right headlight, the right window, none of this will be seen. Only whatever is in this field of vision will be seen. And since I'm using an RP lidar, and which is a two-dimensional sensor, it's gonna give me only the boundary of this car and not the whole, not even a three-dimensional view of it. So, but in the end, you're gonna generate points all over it, and then the points will be reflected back, right? When I'm trying to map the other car. So that's again a point cloud. So yeah, so basically one more thing. So I said that the stereo cameras will combine the images to give a disparity image, and from the disparity image you get the point cloud. So what exactly is a disparity image? So disparity image is an image. It's a two-dimensional image where so each and every point in the image can be either varies, is a transitional, has a transition from black and white. It can be completely black, or it can be gray color, or completely white. Okay, so this colosseum is not a disparity image, because it has all the brown, gray, like orangish color all over it. But the disparity image will be made up with only black to white. It's either like black, gray, kind of thing. So the value varies from 0. 0 corresponds to white, and 255 corresponds to black, or it could be the other way around as well, depending upon your needs. But like, so it's either 0 either corresponds to black or white, or 255 corresponds to either black or white. I'm not really sure of that, but either way, it varies. Each and every point in this in a disparity image varies from 0 to 255. And for example, 255 by 2, that's approximately 125, would be half white, half gray. It will be kind of a grayish kind of a color, which is neither too black or neither too white. So there's a transition between the 0 to 255 depending upon how far that point is. So suppose assuming the Roman Colosseum, again assume the same image. So this can you see my cursor over here, like my cursor, right? So this part of the Roman Colosseum is near to me compared to this part of the Roman Colosseum. That is, this is completely almost like one diameter away from this point. So this point is much closer to me than this point. So if I had referred to the disparity image of this Colosseum, then this point would essentially be kind of I should say kind of whitish, not too white, but more on the whiter side, whereas this point would be more on the blacker side. This point is completely black because it's out of the range of my sensor. If my sensor maximum range has been crossed by an obstacle, that'll be completely black, because obviously it's assuming that there is no obstacle there, so it's completely black. But this obstacle is very near to me, so it'll be kind of very white. this is quite far to me, so it will be kind of blackish but not completely black. So the disparity image, each and every point in the disparity image or pixel basically tells you how far away that object is depending upon the color of the pixel in the disparity image. And once you have the disparity image, you convert it into a point cloud. You're gonna put color to it. You're gonna put color like the normal color whatever is there, and then you're gonna obtain the point cloud. And as I said, you can hover around the point cloud and see all the places properly if you have a VR headset kind of a thing. So that's essentially basically the main functionalities of these stereo cameras. Again, these two are also used for the purpose of simultaneous localization and mapping, that is SLAM. Since these two also have like lenses, they are also used as cameras just for taking images for the purpose of processing as well. So these are multifunctional. They're not just proximity, distance, orientation sensors. They're also act as cameras as well. So that's the main agenda I wanted to cover with respect to proximity, distance, orientation sensors. Obviously, see, like whatever I'm telling you is like the very basic stuff. There's just so much more, like depending on whether you guys are interested in a specific domain, I would highly recommend you to dive deep into the domain and explore it further, because each and every single thing has so much depth into it. So you need, I'm not using a pun over here. Not that I'm not talking about the depth as in how far away this is, but each and every concept has so much of subdomains, and there's so many intricacies behind it, and each one of those intricacies contribute to the domain of robotics as a whole. So that's very important that it's always good to know everything, but what I would suggest is pick the domain which you really love and which you're really passionate about after going through the every single domain briefly, and then just explore it in depth, because whatever I'm doing in this session, most of these sessions are just scratching the surface. There's just much more to it than just the basic introduction. But yeah, this is like a basic overview of the proximity / distance and orientation sensors. So the next thing is the light or image sensor, and yeah, these two fellows are also here as well, obviously, because they act as cameras and image sensors. But can you tell, this is you guys all know what this is, but can you guys tell me what this is, on the complete right?
Camera for a Raspberry Pi.
Yeah, exactly. So this is a Pi camera, camera for a Raspberry Pi. So as you can see, this ribbon kind of a structure over here, right? So the Raspberry Pi has a slot. I can't recollect the exact name of the slot right now, but yeah, it has a slot where you can connect the ribbon, and you can use the Raspberry Pi, and when you boot it on, you'll be able to recognize the Pi cam, and you'll be able to use the camera with the Raspberry Pi for various automation purposes as well. This is of course a normal USB webcam where you connect this to a USB port, and it's either plug and play. You can either sometimes the operating system which you guys will be using will already have drivers ready made for this sort of hardware, but if in case you don't have drivers installed for them, you might have to download or buy drivers which is proprietary to the specific camera you're going to use, and then use it for your own needs. And this again is the stereo cameras which act as cameras and image sensors. Okay, so can someone tell me how long has it been since the session started? What's the time right now?
6:50.
Okay, cool. Yeah, that's fine. I just want to make sure I'm not going too am I going too slow? Am I going too fast? Are you guys feeling comfortable with this pace? Do I need to speed up or speed down?
It's proper.
Okay, cool. Sorry. Yeah, so you guys remember me telling about this thing, right? That each and every domain in robotics is an ocean of its own. So this again brings me to another concept which is extremely widespread, that is computer vision. So computer vision, everybody knows how gigantic the topic is, like this amount of research going on, the amount of applications it has in the real world is pretty huge, especially in robotics. So obviously these sensors which I've been talking about are used to capture images, right? So but once you take images, you obviously when you in computer vision, you can or you may or may not use machine learning or neural networks and deep learning concepts with the images which you obtained. There, even without the usage of machine learning / deep learning, you still have a lot of applications in computer vision. So this is just I'm just going to give you a brief overview of the the data, like what happens once the the image is captured by the image sensor. So as you can see in this picture, the top left corner is basically the origin, and it's the positive y-axis is from the top to bottom. Okay, here they've taken x-axis, but yeah, you can take it as x or y-axis. I personally use it as a y-axis, and then I usually take the x-axis to be from the top left to the right direction. So the thing is, so once you capture an image, right? An image is nothing but it's a series of points, or as we call them, pixels. So each and every square block you see here is a pixel. Okay, it's called a pixel. The thing is, the pixel depends, like the characteristics of each and every pixel depends entirely on two things. That is the illumination and the reflectance of light. Okay, I'm not going to go technical, but it's basically when light hits an object and then comes and hits the lens of the camera, that's when the pixels characteristics is obtained. So depending upon the electromagnetic wave, which specifically that wave which reflected off an object and came and hit your lens. Sorry. So yeah, using the depending on the illumination, the reflectance, and various other characteristics and environmental conditions, each and every pixel will have its own characteristics. So one of the most popular ways of representing a pixel is like color. That is which color is the pixel made up of. So you can't really define a pixel using just one color. So we commonly use three colors. That is RGB: red, green, and blue. So the thing is, each one of those values each one of those values specifically can vary from 0 to 255, where 0 corresponds to the least magnitude, and 255 refers to the highest magnitude of that specific color. So an basically a proper combination of RGB can give us a specific color for a specific pixel. The thing is, people started realizing that using RGB is quite inconvenient. Can someone tell me why RGB is kind of inconvenient? I'm sorry. Like as I said, each one of those RGB will have 0 to 255 values. So 255 into 3, that means I'll have to keep adjusting value 3 times whenever for each pixel, right? So red, green, and blue, each one of those has some value between 0 and 255. So sorry. In order to prevent that from happening, people started using grayscale. Grayscale essentially stands for basically the disparity image kind of a thing, where the whole thing is 0 to 255. That's it. Just one value, which is 0 to 255, and the color is transitioning from black to white. You can also use HSV, that is hue saturation value also. Okay, so the HSV is also another way of representing each and every pixel. I'm not going to go into complete details of what HSV is and the formula to find the saturation, the formula to find value, but if you guys are interested, you can definitely look up on that as well. So basically, once you find the representation for each and every pixel, you can completely represent each and every pixel in the whole image, and then the whole image will become visible to you. So this is like the basic introduction to how to process an image. But the thing is, image processing also has various other techniques, that is converting this so the coordinates is basically present in the spatial domain. You can convert it into the frequency domain, where the frequency of the values, the pixel values being repetitive and the frequency of those values, etc. You can convert it to various domains. You can do convolution and other mathematical operations in the various domains. You can also reduce the area of basically the smaller each and every pixel, the area of each and every pixel, the more accurate the image will be, because the more smaller the pixel area, that means the resolution is better. So that's when we say the image has a good resolution, when the area of the pixel is much smaller than, like, is very small. The more bigger it is, then we say there's a lack of resolution of the image. So that's like the basic introduction. There are more concepts like blurring an image, that is smoothing or blurring of an image using various blurring techniques, edge detection techniques, corner detection techniques, and yeah, so much more. If I go on to, I can actually take a whole session on image processing just for that. So again, this is another very important aspect as well, and in robotics it's extremely important because almost every single robot needs computer vision. Without computer vision, it might not work out. So the thing is, these things, right, whatever I've explained to you right now is what happens when you use an image sensor or a light sensor. But if you're going to be using a lidar and you're going to do SLAM, or you're going to use a lidar or a stereo camera, but you're not going to use the stereo cameras, the lenses, but you're going to use the point cloud, only the point cloud. Then there are other techniques which basically the processing can be done only on point clouds alone and not on images which are taken by camera lenses. So there are again various techniques for recognition and identification using machine learning or using deep learning techniques on point clouds as well. So maybe you guys can look at that also. The next is temperature humidity sensor. I mean obviously all of these are temperature sensors or humidity sensors, or maybe combined as well. But can you guys tell me the name of this one and this one? These are most commonly used ones. Hello, I hope I'm not boring enough. I hope I'm not boring you guys. Are you guys there? Hello?
Yeah, but I don't know any of these sensors.
Yeah, that's fine, not a problem. But
Is the first one a humidity sensor?
Yeah, the first one is a humidity cum temperature sensor. It senses both temperature and humidity. The thing is, yeah, guys, also just let me know if you guys are feeling any difficulty, or should I pause or do slowly and stuff. I'm sorry. Yeah, so the first one is the DHT11 temperature / humidity sensor. The second one is DHT22, and the last one is TMP102 temperature sensor. So all of these are either sense purely temperature or humidity also, depending upon the uses. But yeah, see, technically, like in robotics, temperature sensors and humidity sensors are not usually used as much compared to image sensors or proximity sensors and stuff like that. But you can definitely make a lot of automotive systems using these sensors as well. All of these can be connected to a microcontroller like the Arduino or the Raspberry Pi and work with, or a processor like the Raspberry Pi and work with. So I'll give you a brief explanation of how these sensors work. But yeah, before I do that, I want you guys to try and explain me how you guys think a temperature sensor could work. Like, how can me if I strike a match and then the match lights up with some small amount of fire and I put it near a temperature sensor, how exactly do you think that the processor will get to know that the temperature is increasing? It's fine. See, it's an interactive session, guys. Please talk. It's fine. There's no need to be shy. It's very important to make mistakes and then learn. I'll give you some time. I'll give you a few seconds. Just think, and even if it's wrong, please, like, it's totally fine. No one's gonna judge you.
Are these close range or long range sensors?
These are not long range sensors. They usually need the temperature to be brought very close to them for them to work.
Okay, then I think I remember reading about this a few months ago. There was this is the temperature detected by a series of alternatively n-doped and p-doped semiconductors connected in series throughout the board?
Okay.
Or is it by voltage
Yeah.
fluctuation?
Yeah. So the thing is, no, semiconductors are definitely used in all of this, but for the main purpose of the temperature initiating a response, the voltage fluctuation is actually the main reason. But once the voltage fluctuation happens, the semiconductors definitely do take a part, and they are used in the VLSI requires the semiconductors to operate properly and convert the electrical, the whole physical to electrical signals, and basically transmit the electrical signals from one place to the other place. But yeah, so conductors are definitely used, but the main the initiation being done is using the variation in the voltage. I'm sorry. Yeah, so yeah, basically when the temperature rises, there's a there's a reference junction and measuring junction, right? So when the temperature increases, the due to the difference in the in the temperatures in the junctions, what happens is there is a variation in the voltage. Okay, because resistance kind of changes, right? So you guys know that the resistance and temperature are kind of interrelated to each other, right? So basically when you increase the temperature, the resistance varies, and on one side the resistance remains the same and the whole junction is cold and it remains the same, whereas the other side it becomes hot, and due to this the voltage fluctuation occurs. And because of this voltage fluctuation, the logic design made in the sensor ensures the proper electrical signal is being sent to the controller, thus indicating what the temperature is and what's the temperature change happening. But again, this is very this is a very brief explanation. A proper explanation you guys can go through, and if you're interested in this. Yeah, these are, I mean, yeah, I due to the lack of time, I can't really explain much more about sensors. So I would like you guys to just we'll finish it off by identifying a few more important but very cool sensors. Can you guys tell me what these are?
First one is a multimeter.
Yeah, correct. First one's a multimeter.
Second one
The
is
last one is the
humidity
microphone.
sensor for soil.
Yes, the last one is a sound sensor. It's the microphone. Yeah.
Second one is humidity sensor for mud, soil.
Yeah. It's actually, yeah, you can say it's a soil moisture sensor. Yeah, humidity sensor for soil is also correct. Yeah. Third one is something which we usually use in drones and stuff, or maybe it's
Gyroscope.
sorry.
Gyroscopic sensor.
No, it's not a gyroscope. No, it's not a I mean, yeah, we use gyroscope in drones as well. Okay.
Is it for altitude and stuff?
No, actually, so okay, let me give you another hint. The third one is actually measures a physical parameter. It's more of a physical thing, like a mechanical thing.
Air pressure?
Okay, yeah, you're close enough. It's a barometer, a pressure sensor, basically. It measures the air pressure and the pressure. Sorry. Sorry. Yeah, so it's a barometer which measures the atmospheric pressure. So the multimeter, soil moisture sensor, barometer, and AVR peak sound sensor as well. Multimeter measures various things like current, resistance, capacitance, and other electrical parameters. And this is the soil moisture sensor and the microphone. So yeah, that's pretty much it for sensors. That we've just basically scratched the surface, but yeah, if you guys are really interested in something, definitely do go check those specific sensors out, and their data sheets out and stuff like that, and you guys can learn more about them. So yeah, big actuators again. An actuator is basically a device which is responsible for the movement or actuation of a system or a mechanism, which basically is according a pretty simple definition. We all know that we've all seen, there are various actuators which are can be classified into electric actuators, hydraulic, and pneumatic. But since I mean, due to the lack of time, we will be focusing on electric sensors in this session. However, you guys can definitely feel free to check out every single type of actuator there is being used. So the electric actuators are again classified into rotary actuators and linear electric actuators. But to be honest, electric actuators by default are rotary. The linear electric actuators usually are driven by rotary electric actuators. So this is an example of a linear electric actuator. Sorry. Yeah. So basically, as you guys can you see my cursor? Are you guys able to see my cursor? I'm moving it around in a circle right now.
Yes.
Yeah.
Okay, cool. So this green color thingy here is basically a rotational actuator. It's a rotary actuator. This is the power supply wire. So once you give power supply to this actuator, what happens is the rotary actuator rotates, and there are, as you can see, there are a couple of gears over here. So this gear rotates because of the rotation of this rotary electrical actuator, or also called as a motor, basically. The motor rotates and then this gear rotates, and because of this gear being connected to this gear also rotates, and there's a screw structure, which basically if you guys all used screws, right? So once the screwing mechanism happens over here, the screw is the whole the piston like structure is pushed forward. There's a translatory motion occurring because of the screwing motion. So thus what happens is this end effector essentially moves forward and backward depending upon the polarity of the power supply given over here. So the motor rotates in the specific direction, and then thus this ensures these gears rotate in a specific direction, and according to that direction of screwing, the final end effector moves forward or backward. This is basically a linear actuator, but I have personally never really used a linear actuator myself for any of my applications, but I would suggest you guys to check it out if you are interested. But as I said, so what is this rotary actuator which is used over here? It's basically called a motor. It's an electric motor. Sorry. Yeah. So electric actuators by default usually are motors, right? So we all know what electric motors are. Everything, the fan which we have at our home, the washing machine which we use, the mixie grinder which we use, the vehicles which we drive, everything, all of those have motors, but not all of them. All of them may not be electric motors. Some of them might be just purely mechanical motors. But yeah, essentially what I'm saying is they might be purely driven mechanically. But here the main focus is the electric motors. So this motor is something which you guys can find easily if you go to a shop in SP Road and say, "Bhaiya, give me one ditkodi 100 RPM, 200 RPM, 300 RPM do DC motor kodi," and if you ask, they'll give it up to you. This is essentially the most common DC motor which you can find. So the one in the middle is a BLDC motor. Can you guys tell me what BLDC stands for? Yeah, it's a brushless DC motor, and this third one is a coreless motor. So can you tell me what's the difference between these three motors? What do you guys think is the difference between all three of these?
The middle one is more powerful, right?
Middle one is faster.
Okay. Yeah, that's good. Okay. What next?
Middle one runs on 3-phase AC.
Okay, that's pretty good. Yeah, correct. That's nice.
The first one has a lot of torque.
Okay. Yeah, that's nice. That's nice.
Third one has a lot of speed but less torque, used in small drones or something.
Yes, that's correct. You're absolutely right. So in terms of the internal structure, right, the first one has something called as brushes. It's a brushed DC motor. Okay, so the second one and third one, they don't have brushes. That's why this is a BLDC motor, brushless DC motor, and this essentially doesn't even have an iron core inside it. Forget a brush. Okay, so that's why it's called a coreless motor, because it doesn't have it. Basically, it's a permanent magnet, and the permanent magnet is wounded by a rotor, and there is no iron core present whatsoever in this whole motor. So because of the absence of the iron core, this motor is very efficient and very the acceleration is pretty high and very fast, but the only problem, as you said, is the torque is very less. It can't really drive heavy loads as such. Okay, so that's why it's used on very small miniature drones and racing drones, etc. So yeah, it doesn't have an iron core in it, nor does it have a brush. This BLDC motor, okay, in terms of power, again, how powerful the BLDC motor is compared to this DC motor is actually depends a lot on this thing over here. These two alphabetical letters. These two alphabetical letters is kV. So when you look at this, you'll be like, wait, isn't kV kilovolt? So can I give 1000 kilovolts to this motor? That's what the initial thing is, but confusion happens to all of us. But yeah, it's not kilovolt. kV here stands for I'm sorry, the number of rotations of this motor per volt for 1 volt of supply to the motor. So basically there's a reason this BLDC motor is, even though the word has brushless DC motor, it actually isn't completely DC, because as you can see there are three phases over here, right? So I don't want to use technical terms, but I'll just tell you a basic thing. So in a BLDC motor, what happens is electronic commutation happens, and thus when you supply a DC supply to the BLDC motor, there's an electronic speed controller which converts this DC to AC and then gives it to the motor. So this comes on the BLDC motor comes under a specific category of AC motors called as synchronous motors. Okay, so synchronous motors are motors which always rotate at a specific speed. You cannot like for example, if I use this 100 rpm DC motor, I can't drive it at I can drive it at 50 rpm, 1 rpm, 2 rpm, or even maybe 100 exactly. But this one, once it sets 1000 kV, that means if I give 1 volt of voltage to it, then the rpm, that is 1000 rotations per minute, is guaranteed. Okay, it will always, the speed is always going to be in such a way that 1000 rpm. So if you want the speed in angular velocity, it's 2 pi into the rpm by 60. So that's basically the fixed angular velocity what this motor is gonna have when it's rotating continuously. So you can never force it to change its speed by like half the speed or quarter of its speed. That's why it comes under synchronous motors. And it's not a DC motor. It basically takes in AC, the 3-phase AC, and then it's driven. So also one more thing, if I want this motor, right, suppose if I connect an electronic speed controller to these 3 windings and I connect a battery to that, and this motor starts rotating, what would I need to do in order to change the direction of the motor? So all I need to do is I should interchange any of these 3 wires. So suppose this is assuming all these 3 are connected to the ESC. If I interchange this to here and this to here, then the direction of motor will reverse automatically. The internal circuitry of the motor is made in such a way that change in polarity will change the direction of the motor of any 2 wires of the 3 wires over here. So that's how it's the internal circuit is done. And again, so yeah, as I was saying, the kV rating determines the torque and the RPM of the motor. So higher the kV rating, higher the RPM. So usually, for example, I'm sorry, sorry, I'm speaking for quite a long time. That's why I'm getting some. Yeah. So 1000 kV rating. So usually when kV ratings can go even up to 2500 to 2700 kV rating also. So those motors are like extremely fast. The RPM is so huge that the torque which they can develop, right? So suppose if I want to drive, if I want to put a propeller on this motor, so suppose I'm going to use BLDC motors are very, very commonly used on drones and quadcopters, hexacopters, etc. So suppose I want to put a propeller on this specific BLDC motor, the propeller, if it's too long and if it's too big and heavy, I really shouldn't be putting it on a motor which is like 1000 to 2000, or maybe and definitely not on motors which is 2000 plus kV rating, because what happens is that as I said, if I assume the motor is 2200 kV rating, it has to rotate 2200 rotations per minute for 1 volt of this thing, right? So give me 1 second. Sorry. Yeah, sorry. So basically it has a fixed speed of rotation, right? So I can't necessarily, so suppose I put a very heavy load on it, what happens is this motor will try to continue with that same speed, because it's a synchronous motor, right? It has to rotate at that fixed speed, otherwise it will try its best to get to that speed once you start loading it more and more. But if due to the extremely heavy load, it still may not be able to come to that RPM, because when you put such a high load, the motor might not be able to reach that RPM once again, and when that happens, the motor will definitely burn, and the whole motor will stop functioning completely forever. The permanent damage will occur in the motors. So that's exactly why heavy loading should be done on motors, BLDC motors with lower kV rating. That is usually like 500, 600, maybe even 200, 300 kV motors. Those motors rotate with a very less RPM, than thus the torque. So the torque which can be generated from those motors are pretty high. But then compared to the motors, BLDC motors, which are very high RPM. DC motors, they definitely, again, 100 RPM is not is very less. You can also buy motors with 200, 300 RPM and all those things. Sorry, yeah, but then again, the loading depends upon the since the DC motors are not synchronous motors. It's not necessary that they have to run at 100 RPM only. They can run at 50, 20, 30, anything. So even if a situation occurs that the speed should reduce a bit, right? It can definitely reduce a bit. It's not that there's any harm in reducing the speed of this DC motor. So yeah, that's like the basic overview of electric motors. Okay, yeah, I forgot to tell one more thing. That's a very small thing. So brushes, right? So this is brushed, this is brushless, and this also brushless. The main reason why these two motors do not have brushes is because, as you guys know, these two motors can usually be at very high RPMs, right? This is very high. This obviously has a very high RPM, and 1000 kV plus is also pretty high RPM. So, and they'll also be used for longer hours, because when you use these kind of motors on drones usually fly for a good 15 to 20 minutes, depending on the application of its use. So if you're going to be using these motors for that long of time, there shouldn't be any sparking happening inside the motors. Sparking happens due to the existence of brushes. Okay, so the only reason why the disadvantage of the brushes in this motor is because of the sparking effect which takes place. To avoid sparking, that's the main reason why these two motors don't have brushes. So yeah, I'm not gonna go into depth by explaining you what commutation is, and what exactly and how do you relate the kV rating to electrical parameters and all those things. That's gonna take too much time. But yeah, this is like the basic definition and the basic overview. So the reason why I put these two motors separate of this, there's a reason why I've separated these two motors from these three motors. Can you guys guess why? Okay, do you guys know how these motors operate, the servo motor and the stepper motor? Yeah. Can someone tell me?
Servo motor works for a certain particular angle. It just turns to a certain angle and then stops.
Okay. And how exactly do you suppose I've connected a servo motor to my Arduino microcontroller, how do I allocate a specific angle to it using the code? That's fine. So if you guys want me to give you some time, I can do that, or I can tell you the answer right now. Okay, shall I highlight the differences now?
Stepper motor can be like turned 360 for like and has a greater accuracy, and servo motor only 180 degrees.
Yeah, that's correct. That's absolutely right. But however, why am I separating these three motors from these two motors?
These two you can set the angle at which they're turned. The other three will just rotate.
Okay, no, okay. How about okay? Yeah, that's actually that's a partially correct answer. But the main reason why I'm doing is because of this. What exactly is this?
Pulse width modulation.
Yeah, exactly. So, these motors, right? That is the BLDC, coreless, and DC motors. I can't necessarily directly use pulse width modulation on them. However, on the stepper motor and the micro servo motor, you need to generate PWM signals to actuate these two motors. So, for those who don't know what PWM is, I'm going to explain it right now. So, but yeah, but the answer was almost hitting on the spot. So, the answer is the angle with the angle can be specified to these two motors mainly because of the PWM which you're going to be generating here. So yeah, so as you people would have learned in the past two sessions, a microcontroller or a processor like the Raspberry Pi, they can't generate for example 4.8 volts from the GPIO pins, or even the Arduino Uno or stuff like that. In some microcontrollers like the Node MCU and the Arduino, you can get 3.3 volts as an output or 5 volts, but you can't really get stuff in between that. You can't get 4.5666 volts. So in order to get that voltage, we usually this concept called pulse width modulation, that is PWM. So in PWM, so the this basically voltage versus time. Okay, so the voltage is always 5. I'm assuming it's 5 volts for now. So it's 5 volts over here. Okay, this line corresponds to 5 volts. This 5 volts, and this is also 5 volts, and this is 0 volts. So it can be either 5 volts or 0 volts. That's basically either 1 or 0. So now to generate 4.8 volts, I cannot generate 4.8 volts instantaneously. So what I'm gonna do is I'm gonna try to generate 4.8 volts throughout a duration of time. So for example, say I want to generate an average of 4.8 volts for 10 seconds. So how that works is the sorry, yeah. So my microcontroller keeps on switching on and off the output voltage of 5 volts regularly. So for a small amount of time it's 5 volts, then it suddenly becomes 0 volts and stays 0 for some time. It again becomes 5, it again goes down to 0. So this basically, and yeah, you should remember that the time taken between switching it on and switching it on once again is a constant time. Okay, so this is basically called as the time period, and this is the time period, and this is a single cycle of the PWM operation. One cycle is switching it on, switching it off, and switching it on once again, and this time is pretty much going to be the constant throughout the switching operation. So what happens is once you switch it on for some time and then you switch it off for some time, and you're gonna try to calculate the average voltage throughout this whole time, it's gonna be lesser than 5, because it's basically an integration of 0 to the this is assuming this is T1, this is T2, integration T1 T2, the net voltage is and assuming this is basically uh, T dash, so integration T1 to T dash 5 volts and plus integration T dash to T2 0 volts, and this whole thing is average divided by the whole time period, that is T time period. So in that doing that, you're gonna get the an average of voltage which is not going to be in between 5 volts and 0 volts. And this X voltage, the end product, depends entirely on at what time are you gonna switch this 5 volts off. If you're gonna switch it off way too early, then the an average voltage will be lesser. It will be somewhere around 0.5 to 1 volts or something like that. And if you're gonna switch it off very late, it's gonna be very close to 5 volts in the end. So that's basically essentially how pulse width modulation PWM works. So basically, yeah, the stepper motor and servo motors, right? So essentially, you're going to be giving it PWM signals, and depending upon the PWM signal which you give, the rotation and the angle are going to be mapped and specified respectively. Okay, and last we're going to come to communication protocols. I know I've taken a lot of your time. I'm going to try to finish this fast without really being too fast, because I want you guys to understand this. Sorry. Yeah, so you guys know a lot of sensors, a lot of actuators, but now communication protocols are, as I said, need to be established between them in order to properly, allow communicate. So that, for example, let's take an example what I took earlier. I wanted a burglar alarm, okay, or I wanted an automated fan which will switch on when the temperature of the room is very hot. Sorry. Yeah, so what do I do in that scenario is I need a sensor, I need a microcontroller or a processor, and then I need a motor which acts as a fan. But in order for all these things to work properly, I need to establish a communication between the microcontroller and the sensors and the actuators to form a network. I do this using various communication protocols basically. So again, communication protocols can be either wired or wireless. The wired communication, which I mean, there are extremely a lot of wired protocols used nowadays. I'm going to be going through the most common ones, that is the UART, SPI, and I2C. So UART stands for Universally Asynchronous Receiver and Transmitter. SPI stands for Serial Peripheral Interface. I2C is Inter-Integrated Circuit. So this is a basic block diagram of how UART is going to look like. So UART is basic. Okay, so suppose you guys might have worked with a few sensors which basically use UART. Like for example, if you guys used this thing, what is that? The Bluetooth module, right? The Bluetooth module for your Arduino. The Bluetooth module has to somehow communicate to the microcontroller. It usually uses UART. It uses UART communication essentially, because the Bluetooth module has uh, a transmission pin, a receiving pin, and a 5 volts and a ground, whereas the microcontroller Arduino also has a transmission and receiving pin and a ground. So what happens is the transmission pin of the peripheral or the Bluetooth module is going to send the data to the receiving pin of the microcontroller. And if any I mean, the microcontroller doesn't usually write and send anything to the Bluetooth module. But suppose there was some other not sensor, but some other peripheral, or suppose, okay, yeah, consider two Arduinos interacting with each other using UART. Okay, so then the one Arduino's receiver is going to keep receiving the things transmitted from the other Arduino, and this Arduino is going to keep receiving this stuff from this. So it's basically transferring of data from transmission to receiving and TX to RX continuously. The reason why it's called asynchronous is because you're not going to be using any sort of synchronous kind of way of method of sending messages. It just keeps on happening randomly without any track of time. So in synchronous communication, you use something called as a CLK clock. A clock is basically a series of pulses. It's basically a PWM signal, something like this. It's 5 volts, 0 volts, 5 volts, 0 volts kind of thing. Pulse generated, which can basically help in synchronizing communication. So yeah, this is asynchronous, and this is how UART works. Sorry. Yeah. SPI is serial peripheral interface that basically before I explain this diagram, I'll just explain the terms to you. The SCLK basically stands for serial clock, and as I said just now, a clock is basically a series of pulses of 5 volts and 5 volts regularly at an equal time interval. So SCLK keeps sending, is basically connected to the SCLK of all the slaves. So MOSI stands for master out slave in. Okay, master out slave in. MISO stands for master in slave out, and this is basically a chip select pin. Okay, so I'm going to explain this properly. So usually in SPI can be communication between just two different devices. Suppose, okay, just assume you have two Arduinos and you want to establish communication using SPI between the two Arduinos. So you will usually use one Arduino as the master, that is SPI master, and one Arduino as the SPI slave. So the master should always keep sending the clock pulse to the slave. Okay, so that's how it works. And sorry. So depending upon the clock pulse being sent by the master to the slave, only the data is synchronously sent and received by the systems accordingly. So MOSI is master out slave in, which means the master is sending something out from this pin, and the MOSI pin on the slave is gonna receive the the data which is being sent by MOSI in the master. The MISO in the master is gonna receive data which is being sent by a slave, and the MISO, the MISO on the slave. The chip select is basically, I'll tell you guys why we use the chip select in a while. So this is just assuming two Arduinos or two systems, but SPI allows us the facility to use multiple slaves and not just one slave. The master has to be just a single master. You can't use multiple masters in SPI, but for a given set of slaves. But you can definitely use as many slaves as you want, provided you have the pins and the peripherals to make the proper connection. So the clock is kind of like shorted to each and every single SPI slave. So that's why it's called synchronous communication. Every single thing receives the data exactly at once when the clock pulse becomes 5 volts. The MOSI always goes to the MOSI of the slave, and okay, so this is one way of connecting. Here, see, as you guys can see, what they've done is the MISO of this, they've connected it to the MOSI of another. Okay, in this diagram, this is one way of doing it, and in the end the MISO of the final slave goes to the MISO of the master. But the another way of doing is connecting the MOSI to every single MOSI of all the slaves, connecting the MISO and shorting it to every single MISO of all the slaves. So essentially like that's another way of connecting it. So essentially what happens is when a clock pulse triggers the slaves, only then the MOSI data can be sent to will be accepted by the MOSI of the SPI, and then the MISO can be sent and stuff like that. The chip select essentially, so the thing is, see, I don't want conflict of interest. I don't want multiple slaves receiving everything at the same time. Or if all the slaves send me a data at once, I can't really receive that data at once together. So what do? I have to choose one specific slave to interact with at one point of time. So the chip select, or this actually this is actually SS, that's slave select. Okay, SS slave select, or it can also be named as CS chip select. So it's basically used to figure which slave to focus on at the moment. This is basically a brief overview of SPI protocol. If you a more in-depth analysis can be done by finding stuff on the internet. And lastly, this is the inter-integrated circuit, that is the I2C communication protocol. So the I2C protocol, the advantage of I2C compared to SPI is I2C allows you in any number of masters and any number of slaves. It's not like there's only one master for all the slaves. You can have multiple masters for the multiple slaves you have in I2C. Sorry. Yeah, so how a basic overview of how I2C works is there are basically two very important pins in I2C, that is SDA and SCL. SDA stands for serial data, and SCL stands for serial clock. So again, SCL basically is used to trigger once and sorry, like basically trigger send pulses to trigger the slaves accordingly. So you guys might ask, here there's something called as a slave select, which chooses which slave to interact with.
Here there is no such thing called a slave select. So how does the master, any of the masters, decide which slave to interact with at all? So the answer to that question is the data which is being sent, right, in SDA. The data in I2C protocol always has the address of the slave which it wants to interact with. The address of the slave is already stored within the whole set of the bytes of data which is present in SDA, and only if the address is validated with the current slave which is receiving it, only then that slave will get activated and will interact with the specific master which is sending that specific information to it. And to make the whole process synchronous, the SCL is going to be used. That's basically a brief overview of I2C as well. And yeah, wireless communication, you have like Bluetooth. The most commonly used ones are Bluetooth, Wi-Fi, radio waves, NFC, and similar basic wave medium communication sort of protocols where you use waves of specific frequency and wavelength in order to communicate. This, of course, is like the most frequently used sensors for hobby projects. That is the Bluetooth module HC05. This is the ESP8266 Wi-Fi module. So this base essentially is used to uh, acts as an interface between the microcontroller or processor and a Bluetooth transmitter slash receiver somewhere else. For example, a mobile phone or a laptop, for example. ESP8266 is a Wi-Fi module which is essentially used to connect to the internet. You can actually find this module inbuilt in the Node MCU microcontroller. And yeah, this is the NFC. NFC stands for Near Field Communication. You guys might have seen people use ID cards for scanning, right? Like for example, if you guys have traveled in the Bangalore metro, you might have seen you place your card on this thing on a platform, and it just opens the gates for you, right? So that uses some sort of an NFC communication, an near field communication, where RFID, radio frequency ID tags can be used, or similar tags can be used where the electromagnetic waves and are used for the purpose of identification of specific properties or specific features, and once identified, the algorithm can proceed. That is NFC. And then this is the normal radio frequency transmitter receiver pair for a frequency 433 megahertz radio frequency. So this is again can be used with our microcontrollers, processors, etc., for the purpose of communication wirelessly. Okay, are you all awake, or um have I made you all asleep? Hello.
Yeah. Yeah.
Yeah, sorry for the long session. I try to make it as interactive as possible. If you guys missed out on anything, do check out the recorded session as well. I'll wind up with a few words. Okay. This is the last session of robotics. I'm assuming you guys are in first year, so this is the last session of robotics for yours in your first semester, basically. The next session will be held in the month during the summer, our summer, when you guys will be having your second semester. Okay, so whatever we have covered in the first three sessions, right? It's not really okay. See, I have a lot of, even when I was in first year, I was under the impression that, okay, wait, so this is what robotics is. It's about having sensors, actuators, microcontrollers, or processors, integrating all of them together, and that's robotics. However, that is just a small part of robotics. It's not essentially the whole of robotics. Robotics, uh, okay, to give a brief, like a list of domains which robotics consists of, only the electrical, electronics, and communication aspects have been covered. Like that to the basic foundation of that has been covered in these three sessions what you have attended. Okay, but robotics also consists of mechanical structure design, which is extremely important, which is designing the structure of a specific robot by doing various types of analysis methodologies, etc., and other mechanical tests and research methodologies, which is essentially used to uh, find the most optimal structure, physical structure for a robot. The other type is, and the other domain is obviously machine learning and artificial intelligence. I mean, robots. That's not a prerequisite for robotics. Robots can exist without machine learning and AI and deep learning. However, that's also quite frequently used in robotics nowadays. Another very important domain in robotics is I think I told you this guys a few hours ago, minutes ago. It's SLAM, simultaneous localization and mapping. SLAM, or just localization, or just mapping, is like an extremely huge part of robotics. So the localization and state estimation of a robot is a domain by itself, and even mapping of the environment of a robot is a whole domain by itself. Okay, so that's like you. I mean, there are again multiple subdomains in each and every one of these things. It's very interesting and explore. There's just so many options to, and so many concepts to explore in terms of those two things. And another very important topic which I myself am pursuing my career in is robot motion planning. That is, motion planning of robots is essentially uh, combines path planning of a robot from an initial state to the goal state, and trajectory planning, that is finding the trajectory, that is the velocity, the acceleration, and all those kinematic parameters and the dynamic parameters, and plan the values for those parameters for the motion planning of the robot, and each and every degree of freedom of the robot, for each and every joint and for each and every link of the robot, etc. And sorry, and one more, and the last very important domain of robotics is control systems. I mean, control systems and controls is an advanced topic which you guys would probably learn in your second year or third year depending on your branch. But yeah, that's also another very important part of robots. So this session just covers the electrical, electronics, and communication aspect of robots. So you guys can definitely reach to me or any of the robotics mentors if you are willing to you know pursue a specific if you're willing to explore all the other domains, and even after exploring the domains, if you want to continue with a specific domain and fixate to a specific domain, you guys have any doubts and stuff, you guys can get back to us. So that's pretty much it. And yeah, conclusion is like microcontroller basically has peripherals which enables communication with the sensors, actuators using communication protocols. A sensor and actuator has specifications which can be found by accessing the datasheet of the actuator such sensor. The power supply and the processor and a GPU, if necessary, must be chosen in such a way that the stable integration of the sensors and actuators can be done. Each sensor has each sensor and which I showed you guys has its own API which can be used to access the measurements. And using all these, the basic automated system can be made, which is, again, I repeat, it's only the electrical and electronics aspect of a robot. So yeah, that's it for the session 3. As I said, there are just so many more domains for you guys to explore, so any doubts you can get back to us. I hope you all enjoyed this session, and thank you for attending the session.
Thank you.
Thank you.